All right, folks, we're up to our last section, section 6 of chapter 4, so 4-6, and it's titled Analyzing Isosceles Triangles. So there is, you'll want to have your postulates and theorems handy for this because there are some theorems I'm going to cover here as well as a couple of corollaries. And our first theorem is theorem 4-6. Better known as the isosceles triangle theorem. And in this isosceles triangle theorem, it states that if two sides of a triangle are congruent, then the angles opposite those sides will also be congruent. So they're saying this, they're saying that if we have an isosceles triangle where two sides match, then directly opposite from those sides, so across the way from here and across the way from here, are two angles that would match as well. So if I were to label this A, B, and C, and if I were to explain this theorem in basic caveman talk, it would be this. If AB is congruent to CB, then angle A is congruent to angle C. Okay, the reason that works like that, I can kind of show you here using my compass here. And I want to show you that within a triangle, there's always a direct relationship between an angle and its opposite side. So on this lesson, you do need to understand opposites, because we talked about that previously, that opposite of this side would be this angle, and opposite of that side is this angle. We talked about that on day one when we covered this chapter, when we talked about triangles in general. But there's always a direct relationship then there between an angle and its opposite sides. So if you look at this compass I have here, if I were to close this off, okay, it makes a triangle, right? And I want to show you that this side that I'm using my arm to close off is directly affected by its opposite angle clear over here. Because if I make this angle down here bigger, notice what happened to our opposite side over here. Do you see it got bigger as well? So again, if I were to change the angle, if I were to shrink this down, notice that the side keeps shrinking as well. So there's a direct relationship again with these opposite parts, this side and its opposite angle down here. So it'll only stand to reason then that if we have a couple of congruent sides, then across from them you should have a couple of congruent angles as well. So that's what theorem 4-6 says. Now theorem 4-7 is just the converse of this. So theorem 4-7 is the converse of the isosceles triangle theorem. So in that case, the arrows are going to change up just a little bit here. And also, the statements I made are going to change up a little bit too. So we're going to switch these around. And instead of saying, if the sides are congruent, then the angles are, we're going to say, if the angles are congruent, then the sides are. So the arrows now are going to point the opposite direction here. If these match, then so do those across the way. So AB then would be congruent to CB. See how I switched it around from what we had before? So it works both ways, is really what we're saying. If sides match, angles do. If angles match, sides do. Okay, so those are theorems 4-6 and 4-7. We could even apply that idea on out a little further. You know, the two corollaries that I want to cover are actually based on this same idea. The first corollary is corollary 4-3. Corollary 4-3. And in corollary 4-3, they state that a triangle is equilateral if and only if it is equiangular. So they're saying, remember, corollaries are like a cousin. They're closely related to other ideas. And this is that cousin that likes to take things a step further. You know, everybody's got that cousin that wants to go a step too far sometimes, but always wants to take it a step further. So previously in Theorem 4.7, we said if those two sides match, so do the opposite angles. So across the way from that one was this angle. Across the way from that one was that angle. So what if we apply that theorem not once, but twice? So now this time, instead of using these two sides, you know, what if I said that side is congruent to this side? Now, across from those sides, again, you'd have matching angles. So there's the angle that was already opposite of this one, and opposite this one is that angle. So if I put back in that third side I had marked, if all three sides match, then all three angles must match. We're just applying, like I said, Theorem 4.6, so we're applying it twice. You know, we went across from those two, and then we went across from these two. Okay, but if you just apply it twice, now you can use it for an equilateral triangle as well. And in the statement, by the way, they use the phrase if and only if. Anytime they ever use that phrase, which they used once before, I believe, in our class, I think I mentioned this before, that means it works forwards or backwards. So again, we can reverse the whole thing as well. We can say if I know all three angles match, then all three sides must match. So it works both ways. If all three sides match, all three angles do. If all three angles match, all three sides do. So it's really just theorems 4.6 and 4.7 on steroids, in a sense. You know, we upped it to three sides and three angles. There is also a corollary 4.4, but corollary 4.4, as sick as this may sound, is a cousin of the cousin. So it takes that same statement we made here, and it says in corollary 4.4 that if it's equiangular, then every angle also measures 60 degrees. So it throws that into the mix as well. So now we can say if it's equilateral, then every angle measures 60 degrees. Okay, but the corollaries, of course, are only useful, in this case, these two corollaries only useful for equilateral or equiangular triangles. All right, so those are the theorems and corollaries that are the basis of the problems that we're about to do here in this section. So now I just want to kind of start jumping into the problems themselves. Okay, so let's say that we have a problem like this. Let's call this M, this N, L down here, T there, R here, S here, and let's put some numbers for our angles here. I got a 1, a 2, and a 5 there, 4, an 8, and a 3 there, a 7 here, a 10 here, a 9, a 6, and 11 there. Okay, so in this problem, I'm going to give you some information to begin with, and I want to see if you can figure out the answer here. For example, on this first one, if I told you that if NL is congruent to SL, then you should be able to name for me some congruent angles. Because we learned in this section, of course, that on an isosceles triangle, if two sides match, then there should be two matching angles as well. Okay, so if we mark our sides that we're talking about here, NL was this side, SL is this side there. And remember, theorem 4.6, the first theorem I showed you, said that if these two sides match, so will the opposite angles. So I want you, first of all, only focusing on this smaller triangle in the middle. See how those two sides that we marked are only a part of that triangle? And across from them, opposite of them, do you see our angles 5 and 11? So there's our answer. 5 and 11 must be the two congruent angles on this one. Because again, they are directly opposite of those sides. Okay, let's try it again. This time, let's give you a couple of congruent angles. And then let's have you name for me the two congruent sides. So this time, instead of theorem 4.6, the first theorem that I covered, we're going to use the converse of that. We're going to use theorem 4.7. Okay, so again, I'm going to unmark what I had on my last problem. This time I'm going to mark these two angles, 1 and 4, congruent. But again, the premise is pretty much the same. I want you thinking opposite parts. So if these two angles match, I want you to go opposite of them. And I want you to recognize, first of all, that angles 1 and 4 are only a part of this triangle here. So you should be focusing on MNL, that triangle here. And opposite of these angles would be the two congruent sides. So across from 4 is side MN. And across from angle 1 is side ML. So in a problem like that, if I gave you two congruent angles, you should be able to look across the way within that isosceles triangle with two matching angles. Which, by the way, the two matching angles I forgot to mention, remember on our isosceles triangles are called base angles. So if these base angles match, so will these two legs over here. Remember, the two matching sides are called legs. Let's try that one more time here just to make sure you're catching on. What if I told you that angle 9 is congruent to angle 10? And again, you should be able to name for me then two congruent sides that would be opposite of those angles. So I'm going to erase our old angles from the last problem. This time I'm going to mark 9 and 10 congruent. Okay, so now you need to recognize that 9 and 10 are only a part of the overall triangle. See that? That's the only one triangle that contains both of these angles. So focusing on the big overall triangle, you need to be able to then ignore all of this mumbo jumbo in the center. Ignore all that. So pretend that's not even there now. And now when you look at it without the middle part there, just focusing on the big triangle, I hope it's pretty easy to see that if you went across or opposite of angle 9, opposite of this base angle is this leg, MT, and opposite of that base angle would be that leg, MR. Okay? So just remember, across from congruent angles, opposite of those angles will be congruent sides. And if you already have congruent sides, then opposite of them will be congruent angles. Let's try some other problems here yet. Let me erase that one. And this time, Let's try this problem. We're going to find x. Okay, now be careful on a problem like this. Some of you may be tempted to just go, oh, two congruent sides means two congruent angles. X is 62. Wrong. Be careful. When you look at this one, you gotta, there will be two congruent angles like you thought, but it's not the two you're thinking. You know, if you go opposite of this side, you have this angle. If you go opposite of this side, you have that angle. So that tells me then that x is not necessarily 62, but this angle up here is 62. So those two match. And then do you see that the last angle of any triangle can be found by simply using the fact that all three must add up to 180. So if I add up what I have so far, 62 plus 62 is 124, and I take that away from the 180 for the whole triangle, then that leaves me with 56 degrees for our last remaining angle. So x on this one is 56. So be careful. You know, if those are your matching legs, these would be the base angles, not these. So problems like these can be tricky. You know, here, I'll show you another one. Okay, same deal, find x. Okay, on this problem, again, don't make any assumptions. Go off of the information they give you. If they tell you there's two matching angles, you know that there should also be two matching sides. And those two matching sides should be directly opposite of the angles. So if this angle and this angle are congruent, then across from this one is that side. Across from that one is that side. So on this problem, the 24 is useless information. All I would simply do is say that 3x minus 14 has to equal the 26, not the 24. Okay, and then of course we would add 14 to both sides, and then 30, 40, yep. Then divide by the 3. This one, let's see, 10, 3, comes out to 13 1/3 for that one. Okay, not a nice whole number, but regardless, make sure you set it equal to the 26, not the 24. The 24 in this case was bait, just like over here, it was kind of trying to bait you to say that 62 and x were equal when they were not. Okay, so you'll have some algebra problems like those, and they can even get a little more complicated than some of the ones I've shown you. But on your homework assignment, give them all a shot, do your best, and always keep in mind that across from matching sides will be matching angles, and vice versa. Across from matching angles will be matching sides. Let's see here. Besides the algebra problems then, we're going to do some proofs. You could always use more practice in proofs. Okay, so I've got 2 or 3, I think 3 of these to try with you here to finish out this lesson. And our first one, I actually want to kind of do a proof of theorem 4-7. So this is going to be a proof of theorem 4-7. So of course that means the one thing we cannot use in this proof as a reason is theorem 4-7. Okay, you can't use the theorem you're trying to prove in the proof. Okay, now in theorem 4.7, if you remember correctly, that's the second theorem that said that if we start out with two congruent angles, so I'm going to start out with a picture something like this, where these two angles are going to be congruent from the get-go. So that'll be our given. Angle A is already congruent to angle C. And we're going to try to prove then that the opposite sides are congruent. So in this case, we're trying to show that side AB and side BC would be our congruent sides. Now, in order to pull this off, I'm actually going to add a little bit more into our picture here. Because remember, this entire chapter has been about proving triangles congruent. And currently in this picture, there's only one triangle. One and only one. So what I'm going to do is I'm going to drop a segment down like this. A segment BD. Okay, and in my segment BD then, I'm going to make sure that it does something special as well. Like for example, on this one, I'm going to say that my segment BD is going to be perpendicular. So I'm going to give you that BD is perpendicular to AC. That should be enough now to help us finish doing this proof. All right, so first step, I'm going to restate my givens, including that one I added on. So I'm going to put angle A is congruent to angle C, and BD is perpendicular to AC. You know, theoretically, we'd be able to do that on any triangle that you were to draw like this. You'd be able to drop a height, an altitude at a right angle like that. So it's fair game. We could do this. All right, so I've already marked my angles congruent in my picture. This other given, though, that they're perpendicular, remember that's going to lead to a couple of steps in our proof, because the first step that follows up from this is to say that we have a couple of right angles here. So we're going to state that those angles, angles ADB and CDB, that right angle, I'm going to say that those two at D are right angles. I knew they were right angles because of our given statement that they're perpendicular. So my reason is going to be I'm simply using the definition of what it means to be perpendicular. Okay, remember in our 10 Commandments, if they use a big word or for that matter, a symbol for a big word, then you're going to use that word's definition. But that's not enough. We still have to do one more follow-up step, because if I'm going to prove triangles congruent, I need to show that parts are congruent. Like here, they gave us those angles were congruent. And now I can state that these two angles are congruent as well. So I'm going to do a follow-up step and say that those same two angles, ADB and CDB, are congruent. That follow-up step is always the same reason we've done at least two proofs together here like this. After saying you have right angles, you would just simply say that our reason that they're congruent is because all right angles are congruent. It's an old theorem from chapter 2. I think it was theorem 2.6. Okay, but that does give me now a pair of parts congruent in my proof. So I'm up to two pairs of parts. You can see it in my picture. It's two pairs of angles. The only problem is I've used up all my givens. Okay, so now I have to look back at my picture and see if there's anything else that I can mark congruent just by looking at the picture. And there is something we're supposed to keep an eye out for, and it's when triangles share a side. See that side down the middle? So we can state in step 4 that BD is congruent to itself You remember the reason why we could say any segment is congruent to itself? We could say it by the reflexive property. It's like when you see your reflection in the mirror. Whenever they share a side, that's always going to be your reason, is the reflexive property. And that gives me my last pair of sides, or I should say my last pair of parts necessary to prove the triangle is congruent. Remember, we have many different methods now. We've got SSS, SAS, ASA, AAS, and HL. Those are all 5 different ways that we've learned to prove triangles congruent. And we should be able to use one of those in this situation as well. If I look at my picture, I see I've got 2 angles. So I could already rule out SSS or SAS. Even HL. Remember, HL spells donkey and it has 2 sides, the hypotenuse and the leg. And even though it's a right triangle, we still are ruling out HL, so be careful. So I know it's one of these 2 now, and all I have to do is ask myself, is the side in between the angles, or is the side outside of the angles, not in between? Well, these 2 angles, the side that joins them right here at the bottom would be the side in between, and that is not the side in between. So I'm going to use this method, my newer method of AAS, to prove that these triangles are congruent. Don't forget to make the statement then over here that the triangles are in fact congruent. ABD is congruent to triangle CBD. Again, notice that says triangle, not angle like up here. Some people get that confused. All right, so we're almost done. I've proven the triangle is congruent. I'm supposed to be proving some parts congruent, but once the triangles are congruent, then all of their corresponding parts should be congruent, including AB and CB. So I state that AB and CB are congruent, and do you remember that reason? It's the reason that you can only use after you prove triangles congruent. You always use it to prove parts congruent in a proof. And it's got 5 letters. C, P, C, T, C. If you want to win that toaster oven, tell me what it stands for. I'll give you a sec. Ready? All right, you got your shot. It's corresponding parts of congruent triangles are congruent. Again, you can't use it till you show congruent triangles, and it really just says that the corresponding parts are congruent, which are those sides in this case. Although it could just as easy be angles. Okay, so there's one proof, and that actually proved theorem 4.7, how it works. Remember, all theorems can be proved. So for our next one here, I'm going to give you a picture similar to the one we just had a little bit ago there. This is not a proof of theorem 4.7 though, so you are welcome to use that theorem or any others that we've covered. On this one, I'm going to give you that angle A is congruent to angle C. And I'm going to give you that segment BD bisects angle ABC. And we're going to prove then that AD is congruent to CD. Now, by the way, before I get much further, this does remind me of something. When we want to use our theorems from this section, whether it be 4.6 or 4.7, do keep this in mind. If you have, for example, a picture like this where these angles are congruent, but then I split it like this into two triangles. If you want to use one of our theorems that says the opposite sides match, do not go directly opposite to only to there. Okay? On a problem like that, you need to be able to focus on the overall triangle. And instead, keep going, because the opposite side would be clear over here. And the opposite side for that one, clear over there. Even if there's a line down the middle, you got to be able to see it as one big triangle. Okay, because too many people do that a lot of times in proofs and stuff. You know, if I have, for example, you know, say this side congruent to this, and then again I drop a line, you know, maybe even like, well, that was okay. Yeah, like this. Two sides match, and then when I drop a line like this, then they see, oh, two matching sides, so the opposite angles match. And they want to say those angles there would match. No, that's wrong. You got to be looking at the overall triangle, the big triangle, the isosceles triangle. These theorems in this section only apply to an isosceles triangle. So if you look at it as one big triangle, you should be looking clear over there. And this one, opposite of this, would be clear over there. And even if I drop this, then you can still do that. It's just you got to look at it as one giant triangle, one big isosceles triangle. So be careful. Don't say opposite of this is that one and opposite of that one is that one. Okay? If that was the case, you know, if you could do it on separate triangles, you could have a triangle like this and then another triangle like this. And you could go, oh, well, that side matches that one, so this angle matches that one. No, it's not. You know, just because those sides match don't mean those angles do. You can see this angle is actually a lot smaller than that one up there. Okay? So it still has to be within one triangle. Within one triangle, if that works. All right, with that in mind, let's do our problem here, our proof. Let's copy down angle A is congruent to angle C. BD bisects angle ABC. We write down that was given. And we can mark some of this stuff already in our picture, like angle A congruent to angle C. The other one, though, we got to work with that a little bit. They use that word bisects, and they mention that it bisects this angle. I could care less about this guy. He's the bisector. He's the one doing the cutting. But this one is what I'm worried about. He's the one that's cut in half. So if I take angle ABC and cut him in half, ABC is that overall angle, then I should have two matching halves up there at the top. And that's going to be my step 2, is to state that those two angles at the top are congruent. Don't just say angle B congruent to angle B. You got to be specific. You're going to have to use 3 letters because they're 2 different angle B's. So the first angle would be angle ABD. And the second angle would be angle CBD. Both with B as a middle letter. But I knew those were congruent because they said it was bisected. So my reason is going to be the definition of what it means to bisect. So definition of a bisector. If you want to be specific, you could say an angle bisector. All right, so that gives me 1, 2 pairs of parts congruent so far. You can see it in my picture as well. It's 2 pairs of angles. Okay, my goal, as usual in this chapter, is going to be to try to show the triangles congruent. So there should be one more pair of parts that I can mark congruent here. And if you don't see it, look at the picture. Don't forget on your 10 commandments, it says you should always keep an eye out for if they share a side. See it? BD. So we can say BD is congruent to itself. Remember the reason? Anytime you say anything's congruent to itself, you're using the reflexive property. And that pair of sides then gives me just enough to prove the triangle is congruent. I can see in my picture I've got 3 pairs of parts. So for step 4, I should now be able to state that the triangles are congruent. So again, be careful. I'm going to change from up here, I said angle ABD, to triangle ABD is congruent to triangle CBD. So those state 2 different things. You see that? That's triangles. Look at the picture to see how you know they're congruent. Remember, we have 5 different ways. There's SSS, SAS, ASA, AAS, and HL. Looking at our picture, I've got 2 angles on each triangle. So I could already rule out anything that's got 2 sides. I know it's not any of those, including HL. So again, I'm down to either ASA or AAS. And I see that my side here is not in between the angles. See how the side in between the angles would be the one joining them right here? That is not in between. So I don't want the one in between. I want the one that's not in between. So that's AAS, our newer shortcut. And then on this one, I want to prove these parts congruent yet. So I've got one more step. Once I prove the triangle's congruent, I can now say the parts are congruent. And remember our reason? It's got 5 letters in it. CPCTC. Corresponding parts of congruent triangles are congruent. Again, you can't use it until you prove triangles congruent first, like we did in step 4. There you have it. There's that proof. And I've got one more I want to try with you before I call it a day. So on this next one, I've got a little bit different of a picture here. This time our picture looks like this. There's A, R, S, T, Q. Under our givens, I'm going to give you that AR is congruent to AQ. And RS is congruent to QT. And in the end, I'm going to prove that AS is congruent to AT. Okay. Now, on this problem, I'm going to put for my first step, of course, I'm going to copy down what I was given. Okay, on this one, I know AR is equal to AQ. I'm going to mark it in my picture as well. And RS is equal to QT. RS, QT. All right, that is our given. Step 2. Now, when I look at this problem, This is going to go back to what I was mentioning earlier. I need you to be able to focus on the overall triangle here. So if I were to erase for right now those two lines there, see how it's one big isosceles triangle with two matching sides? Because of that, I can make use of one of our theorems where we can say now across from this side, clear down here, see how that's opposite of that side, would be an angle congruent to the other one clear down here, opposite of that side. Okay, so I'm using one of our new theorems today, theorem 4-6, which said that if the sides are congruent, so are the opposite angles. So I'm saying angle R is congruent to angle Q. We draw those back in because now I want you to see that we've got a triangle right there that has a side, and an angle in between. See it? And it has a matching triangle over there. So now I have 1, 2, 3 congruent parts on each of those triangles. That should be enough to prove those triangles are congruent to each other. So those skinny little triangles like ARS and its matching triangle on the other side, AQT, those have to be congruent. I hope you see by what method. I've got two sides and the angle right in between those two sides. So as you see right there, I'm going to be using SAS to prove those triangles congruent. And then you may notice that AS and AT are a couple of sides that are a part of those. You see there's...
The lost flute has been found at home.
Okay. But this side AS and this side AT are both a part of those two triangles that we just proved congruent. So this one's, believe it or not, just has one more step yet, a step 4, where you can now say that AS is congruent to AT. And they're the last pair of parts, or an additional pair of parts yet on those congruent triangles we just mentioned. So we're using CPCTC. So that one's just 4 steps. Pretty easy once you see how it's done, but it can be a little tricky because how they break up the picture. One thing though, I want to go right back to the proof I did before this. I just realized that there was a different way you could do it. So I'm going to show you that real quick too. And it actually utilizes something new that we did today. So the previous proof, if you remember right, looked like this. Remember, it had angle A was congruent to angle C, and it had BD bisects angle ABC. And we were trying to prove that AD was congruent to CD. Okay, one of the other things that I could have done here that I chose not to, because I had used the bisecting of the angle here at the top, and then I went with the side they shared. But another thing you could do here after you've done that is ignore this segment down the middle, and we could use theorem 4-7, the second theorem of the two that I taught you today, 4-6 and 4-7. 4-7 is the one that says if the angles match, then so do the opposite sides. So clear across from that one and clear across from that one would be those sides. So I could state those sides congruent, AB and BC, using theorem 4.7. Okay? And then I hope you see that previously I had used AAS when we used the side they shared. But now, do you see you could even use ASA? So that would just change that up a little bit. When you go to prove the triangle is congruent, you could then use ASA to prove that triangles ABD and CBD congruent. But then you still would use CPCTC to show that AD and CD are congruent. So it changes the latter part of that proof if you want to go that route. Either one is correct though. Okay, you're going to find that some proofs can be done in more than one way. And sometimes there's longer ways, sometimes there's shorter ways. Sometimes it's the same amount of steps. This one I think would be the same amount of steps if you did this route as well. But I just wanted to show you that you could utilize theorem 4.7 on that previous proof as well. All right, that should be enough then to prepare you for your homework in this section, section 4.6, which by the way is the last section of chapter 4. So this is going to be then the last lesson that I provide for you in our 3-week span. When you get back, then we'll try some review problems on a review sheet to help you prepare, and hopefully then you'll be able to take a test too when you get back, but not on the day you get back. Don't worry. We'll review first on the day we get back, and then we'll take our test. If our timelines change for whatever reason, if this gets extended longer, then we'll just have to adapt accordingly. We'll play it by ear. Enjoy your break.